Now, like I said, this sheet of paper is extremely, extremely important. This is all of Activity 7 on the front and back of that piece of paper. Today we're going to get through Lesson 1 and 2 of 3 from Activity 7. But your homework is only over Lesson 1. The reason I didn't assign stuff from Lesson 2 is just because you also got that proof worksheet. So I want you to focus on that proof worksheet and only the first lesson of Activity 7. Next class, if you can see it written on the board in green ink, it says Activity 7-1 quiz, next class. And so you will have a quiz over Lesson 1, the first part of 3 from Activity 7. Okay. So this piece of paper is extremely important. The first part, it talks about 3 special type of lines: parallel, perpendicular, and skew. I'm sure all of us have heard of parallel and perpendicular lines, but I think that maybe something was left out of the definition when you originally learned parallel lines. And the thing that may have been left out is that parallel lines, yes, they will never intersect. However, they are coplanar. They're in the same plane, so they have to be in the same plane. While skew lines, that may be new to us, those lines also never intersect. However, these lines are in different planes. They are in different planes. Perpendicular, we have been talking about perpendicular lines for a while now. We've used them in our proofs. We've used the definition of perpendicular, so we should be very familiar with that. So an example in the classroom of parallel lines is if you look at this really expensive, rich mahogany wood. Those 2 lines here, these are parallel because they're in the same plane. They're in this wall that is one plane. However, if you were to compare one of these wooden slats, one of these lines to one of the lines of the wooden slats to the back of the classroom, that back wall, those lines will never intersect. However, they're in completely different planes. So that's why we would call those skew lines. But remember, even though that this definition says lines in particular, these also, like parallel, perpendicular, skew, that also applies to pieces or parts of lines, like rays and segments. So you can also have skew segments, skew rays, and parallel segments and parallel rays, and so on and so forth. So don't forget about that. This isn't just exclusive to lines. From there, I just gave you this rectangular right prism, and I identify some examples for you. Now, let's just kind of break this apart and explain why it's important. I tell you that it's a rectangular prism, and also that it is a right prism. It's rectangular because all the faces, every single one of them, are rectangles. But also I tell you that it's a right prism, meaning it's not oblique, it's not kind of shifted. In right prisms, the 2 congruent bases are directly above and below each other. But in an oblique prism, it's where they're kind of shifted off. So the reason I tell you it's rectangle and a right prism, there's just a bunch of right angles happening in this diagram. That's why. Okay? Because I always tell you, you can never assume anything in geometry. So I realized that in this diagram there are no right angle indicators. That little box that tells you that objects are perpendicular, that there are right angles being formed. So I realized that there's none in this drawing, but I'm telling you it's a right rectangular prism. So there are a bunch of right angles in here, even though the marking's not there. You good? Great response. Wonderful. Okay. So parallel lines, again, in the same plane, coplanar, but will never intersect. I gave you line AE and line ZG. So these 2 lines here, I just outlined line AE in red, this one in blue. Those are in the same plane. They're both in that front plane, and they'll never intersect. So that's an example of parallel lines. I want you to find your own example of coplanar lines that will never intersect, aka parallel. Please find your own pair of parallel lines. Seth, what was your example, bud?
Lines GY, ET.
Lines GY and line ET. Absolutely. That is a perfect example. They're both in this right panel, that right side. That's what plane they're both in, and they will never intersect. The notation for this, so right now we're just identifying, we're saying, hey, this line and this line are parallel. But if we wanted to use the parallel symbol, then going with Seth's example, we've got line, that's the notation for line, ET and line GY. The notation for it are two bars that are right next to each other. I make my bars much longer than the notation. Some textbooks it's a little bit shorter, but in the end, the general case is that you have two bars that are right next to each other. That's just saying that those lines are parallel. So this is the parallel notation. Moving down from that, perpendicular lines. Perpendicular. The example I gave you were lines ZH and line HY. So these two lines intersect at point H, and there at point H, a right angle is being formed by those two lines. I want you to find your own example of two perpendicular lines. Izzy, what example did you give?
Line AW and
Line
line WT.
AW and line AT. Very good. So we're going to roll with those examples. So I've got line AW and line TW or WT. I think we're all familiar with the sign for perpendicular, but it is an upside down T. My notation, I also add in a little box right there to be absolutely clear. So that is a symbol for perpendicular. The last example of skew lines. So remember, skew lines, they will never intersect, however they're in different planes. So the two that I gave you were lines AE and line TY. Now I can see a lot of you right now are looking down trying to find your own set of skew lines, but let's just chat about this real quick, then you can find your own. What planes, plural, is line AE in? We don't have to name them, so tell me top, bottom, left, right, front, back. Like what planes is lane AE in? Seth, what's that?
Top, front.
Good. The top, so this plane, plane WAT, and then the front, plane AZE is an example of the name for that. Okay? So make sure that the other line that you create is not in either one of those planes. So that's what you have to think about when you're finding your own skew line. So, okay, now ready, go. You don't have to use line AE though. Just find two completely different lines that are skew. All right, Lydia, what two lines did you write down for skew?
Line WT and line AZ.
Line WT and line AZ. Those are perfect. Those work really well. There's no notation for skew lines. You just have to write it out. So you would say line WT and line AZ are skew lines. Okay, so don't forget this applies with segments and rays. Right below that, on your notes, right in front of you, it says, this is just two examples of each. I gave you one example of each, and you came up with your own example. That's just two of each. There are tons more. Tons and tons more. So if you want to practice, and hey, come up to me and say, Mr. Niven, are these perpendicular? Are these skew? Am I doing this right? If you want to write down more, wonderful. Okay? But this is just two examples of each. Are we all savvy with parallel, perpendicular, skew lines? Do we have any questions about that? Wonderful. Okay. Then we're going to go to the next topic. And this is where we're going to kind of camp out for the rest of the day. And it involves this diagram right here, where you have lines M and N. You have these two lines that are going generally in the same direction. They are going horizontal. Are they parallel? Absolutely not. They're eventually going to intersect somewhere. I didn't put that on the diagram, but we can clearly see they're not parallel. But we have two lines that are going generally in the same direction horizontally. Then we've got line T, this guy that's cutting through. Whenever you have two or more lines that are generally going in the same direction, and you have another one that is cutting through those, that line that's cutting through is called the transversal. The transversal. So over on the left of your notes, it has the definition of the transversal. And what it says is, the transversal is a line that intersects two or more coplanar lines in different points. That last little part, in different points, is very important because I could have 3 or more lines intersect all at the same point. None of those are transversals because not a single line is intersecting 2 or more lines at different points. So this is not an example of a transversal. I want you to add something to that definition, and it'll make sense later, but I want you to write next to transversal that the transversal role can change. By that I mean, in one scenario, a line can be a transversal, and then looking at the diagram differently, that same line is no longer considered to be the transversal. So that role is going to change, depending on how you look at your diagram. And we will talk about that in depth in a little bit. All right, those colored pencils will come into play in just a second. But let's go ahead and analyze this diagram for a second. So we have our 2 lines that are generally going the same direction, cut by a single line, this transversal. There are 2 intersections happening. And at each intersection, how many angles are being formed at each intersection? There's 4, right? So in this intersection of line T and line N, you've got 1, 2, 3, 4, those 4 angles. Then also, when T intersects with M, you've got 4 more angles. I've decided to call them 5, 6, 7, and 8 because we all appreciate everyone. No. Yes. I don't know. You should. But anywho, so we know a lot about that scenario where 2 lines intersect one another. We have been looking at that situation since day 1 in this class. So what I'm going to do is I'm going to take a little note card and I'm going to block off that second intersection. So I'm only considering angles 1, 2, 3, and 4 right now. There are certain classifications of 2 angles, like pairs of angles in this diagram. So we are beyond the point, beyond identifying angles as acute and obtuse. Like I think we all graduated from that. We can all identify acute and obtuse angles. Also, if you claim or if you say that 2 angles are adjacent, that's a good thing that you can recognize that, but that's not going to really tell us anything about their measurements or how they're related to one another. So we're not going to be using that description anymore. But in this diagram, what special types of angles are happening? What's up, Rachel? You got vertical angles happening, right? So Chris, give me an example of vertical angles in this diagram right here.
1 and 4.
Angles 1 and angle 4. That's an example of vertical angles. What do we know to be true about vertical angles always? Do I? Okay, they're congruent. The definition says that they're congruent, meaning same size, same shape, but we know that if 2 angles are congruent, then their measures are equal. So again, trying to train you for proofs, we need to go in the correct logical order. These are vertical angles. The definition states that they're congruent, same size, same shape. And then you know the definition of congruent angles says that those measures are equal. So make sure you're not skipping steps. There's also another pair of vertical angles in this diagram. You've got angle 2 and angle 3. Those are never going to go away. We're always going to be continually using vertical angles to help us solve problems and relate angles to one another. There's another special type of angles in this diagram we've been talking about.